Okay, folks, welcome back to the IWERI Idaho Water Resources Seminar Series. Today, it's my pleasure to introduce Clifford Swanson, who received his doctorate at the University of Tennessee in civil engineering, studying dynamics of the drinking water microbiome, and is currently a new assistant professor up here in Moscow at the University of Idaho in the Department of Civil and Environmental Engineering. And his focus is on risks associated with drinking water, including pathogen growth and contaminant exposures. So again, without further ado, I'll turn it over to Clifford. Please bear with us just a little bit in case there's any technology fumbles, because we're actually broadcasting live from Moscow for a change, rather than having folks in their own offices scattered around the country. So if there might be any just glitches with technology, just bear with us for a little bit here. So anyhow, thanks again to Clifford, and I'll turn it over.
All right. I'm gonna adjust this a little bit if that's okay. It feels kind of weird to like have people in the room and like be talking to the camera. Great introduction, thanks Tim. And I was trying to put together this presentation, and so I do want to go ahead and mention that this is a lot of preliminary work. Instead of showing studies I had done previously, I have a great master's student who put together. He's currently working on his thesis on a project. So this is a great time to actually show what we've done at the University of Idaho. So you'll see a lot of the overarching themes of what I want to do in my research. But again, a lot of this is going to be preliminary because this is still like an active project. Okay. So just to give some background, what is motivating this research and a lot of other research areas I'm looking at is we look at the public water system as a whole. And so in general, when we think of water systems, we generally think of water source and then water treatment. Drinking water becomes challenging because we have several different areas. We have the source water that can be an area of concern. We have water treatment, obviously is a major area. And then we can get significant changes to water within water distribution and within the premise plumbing and point of use. So when we look at these public water systems, we look at a lot of these different areas. When we start talking about like water treatment systems, I think conventionally we think of surface water treatment. So the conventional wisdom for surface water, here you have your source being lakes, rivers, streams. These are generally thought to be high biological activity. That includes a lot of enteric pathogens. Giardia and Cryptosporidium are two major pathogens of concern. This can also include things like harmful algal blooms, right? So generally think surface water is a lot more biologically active, so we have a lot more risks there. As such, we have significantly more regulated treatment for surface water. That is mandated by the Safe Drinking Water Act and the Surface Water Treatment Rule, which requires the use of filtration and disinfection for the purpose of targeting Cryptosporidium, Giardia, and enteric viruses. Part of this is we must maintain a residual disinfection of over 0.2 milligrams per liter as a way of controlling regrowth within that post-treatment system, right? So within distribution, within the premise plumbing. But I mean, across the state, we have a lot of water systems that use groundwater. Conventionally, we don't think of these as being biologically active. There are organisms, they can be anaerobic, they tend to be iron sulfur cycling organisms. These tend to not be pathogenic. Generally, the biological concerns with groundwater is quite low. As such, there is no required treatment. Though many places still maintain some level of residual disinfection, though that is not a requirement. There is no regulation that mandates this. The groundwater rule within the Safe Drinking Water Act just requires monitoring for E. coli, enterococci, and colophages. Misspelling there. But these are indicators for potential fecal contamination. As long as you don't have fecal contamination, there's no requirements for treatment. And so that's a lot of the conventional wisdom for these public water systems. But when we start looking at this, we look at a lot of the current epidemiology behind drinking water diseases in the US. I think generally we think that these are going to be a lot of enteric illnesses related to Giardia, E. coli, or enteric viruses. And the CDC does this great monitoring effort every year. They release a report every 2 years on the epidemiology of drinking water diseases. And for the most part, we see that over the last decade, we have the majority of these outbreaks, cases, and mortalities are overwhelming coming from public systems. So these are systems that do follow the Safe Drinking Water Act, the groundwater rule, and the surface water treatment rule. And so I want to focus on these because these are obviously the systems that have the most impact. They have the most area of concern. So when we start breaking down each of these categories, we can look at the etiologies that are causing these diseases. So overwhelmingly, our outbreaks and mortalities are caused by bacterial causes of illness. I do want to point out we do have some protozoa that are responsible for a significant number of cases as well. We will look at those individually, but a lot of these other things don't really seem to be major contributors. I do want to pause here and make a note that this data set is on acute illnesses. This does not include things related to PFAS or heavy metals. This is just self-reported data to the CDC from state agencies, okay? So obviously, this is assumed to be an underestimation, and it is not accounting for everything, but what is reported, this is the trends we're seeing. When we look at these protozoa, or these protists, we have two major causes. These are well-known, Cryptosporidium and Giardia. They have about similar number of outbreaks. They're quite low. Over this decade, we have about 7 outbreaks from Cryptosporidium. We have 4 from Giardia. Pretty even split between groundwater and surface water systems, so kind of indicating that we do have some biological concern with groundwater. And then the number of cases are just dramatically higher for Cryptosporidium. That is driven by one single outbreak, where there were like 300 people in a groundwater system that had Cryptosporidium related outbreak. The one we really want to focus on is bacteria. That's going to tie in a lot with this work, but we have a lot of these different causes for drinking water illness, but the number one we're seeing now is Legionella. Here, there's a few I want to point out. We have Legionella, non-tuberculosis mycobacterium, and Pseudomonas, and the reason I want to point these out is these are not the traditional pathogens we associate with drinking water. Typically, we associate GI pathogens with drinking water. These are respiratory pathogens, right? Legionella causes Legionnaire's disease, Pseudomonas causes pneumonia, and then Mycobacterium causes a whole range of different respiratory infections. So we are seeing that there is this shift currently with these public water systems that most of these diseases are actually not going to be gastrointestinal. They tend to be respiratory. And it's driven by these 3 groups of pathogens. In fact, I'll refer to these throughout this presentation as opportunistic pathogens. Generally, exposure to Legionella is pretty common, but they tend to affect people that have some sort of immunodeficiency. And we see that these are widely spread through groundwater and surface water. Just as a note, I don't think I touched on this yet. This in our category, those are just outbreaks where the water source is not reported. Okay. So going back, there's this concern with these bacterial pathogens. I make one more note that all the mortalities we're seeing in the U.S. associated with drinking water is associated with Legionella, right? So that is going to be one of the bigger concerns. In fact, there was a major Legionella outbreak over the summer in New York City. So this is a persistent issue. So when we're going back and looking at our public water system, we generally have 3 things we're looking at that is causing these types of issues. 2 of them we can put together as contaminated water sources or improper treatment. They kind of tie together because if you have a contaminated water source but with proper treatment, that tends to mitigate those risks. And then obviously improper treatment can lead to these issues. And the other one, which is the one we will focus on a lot in this study, is biofilm regrowth. So this is actually where you get organisms grow within biofilms of pipes, and then under the right conditions, they can regrow and enter the drinking water, causing exposure risks. So the main motivations we're going to look at in this study is we want to examine the risk associated with both surface and groundwater public water systems. We want to determine how management differences between these public water systems influence that post-treatment risk. And we want to develop tools that examine opportunistic pathogens, further evaluate risk, and characterize distribution system biofilms. Okay, so jumping into the methods we used, we would go through, we had two different public water systems. We had one that was a surface water system and one that was a groundwater system. Our surface water system had advanced membrane filtration. They had extensive disinfection, plus they maintained a high level of residual disinfection. And this was a surface water treatment rule compliant system. Our groundwater system, on the other hand, it was a series of different pumping stations. They would maintain a level of residual disinfection, but they did not do any contact basin disinfection. They did not do any filtration. But this system, I want to emphasize, was groundwater rule compliant, right? They did all the monitoring necessary. They saw that their source water was not contaminated. So both these systems are maintaining a compliant public water system. For both of these, we're sampling over 12 months. We are currently in the process of that, so this will not be the full extent of our data. And we sampled at 3 types of locations. So we sampled the source water, we sampled the treated water effluent, so what was leaving the treatment facility, and then we sampled different points throughout the distribution system as a way of identifying these changes post-treatment. So just kind of visualizing what this looked like, we had sample of the influent to the water treatment facility, we sampled the effluent of the water treatment facility, and then we sampled at different points throughout the distribution system. Okay. So what do we do with these samples? Well, when we first collected samples, we would do a lot of field measurements. This would be things like pH, temperature, and dissolved oxygen. Those are things that can change quite quickly after collecting samples, so we wanted to capture those relatively quickly. We then would take samples back and do some analytical measurements. So this included measuring conductivity, chlorine residual, and alkalinity. We then wanted to quantify the bacterial concentration or bacterial loading in these samples. So we did heterotrophic plate counts as a way of just broadly capturing heterotrophic organisms. We incubated these for 5 days at 28 degrees Celsius, and then we quantified them as colony forming units per 100 milliliters. That just gives us an estimation on the bacterial loading within this. Doesn't tell us pathogens or not, just general bacteria. And then lastly, the bulk of our work was we did some organism identification. Here we isolated biomass, we extracted DNA and amplified the 16S rRNA gene. What this does is this targets bacteria and archaea specifically. So we aren't looking at Giardia, we're not looking at Cryptosporidium. This is just things like Legionella, Mycobacterium, and other prokaryotes. Okay. We did MySeq sequencing here on campus, and then we did microbiome profiling, where again our focus was on potential pathogens, but we also look at microbial ecology with this as well. So I'm going to break this down into a series of stages so we can kind of track the water as it goes through our public water system. So just very quickly off the bat, what are the differences in source water quality, right? We have this presumed water quality composition for surface water being more biologically active, having a lot more like dissolved oxygen, but a lot less mineral content. We tend to assume groundwater has a lot higher mineral content, a lot lower microbial activity. So we just wanted to characterize this. So just breaking down our source waters, we see that trends bear out here, right? So we have a significantly higher alkalinity in our groundwater, about 220 milligrams per liter versus 40 milligrams per liter for surface water. That's to be expected. We see with our conductivity, we're at about 400 versus just under 100. That again is something that would be characteristic of high mineral content. And then we see with dissolved oxygen, with our surface water, we tend to be pretty saturated in in dissolved oxygen. So we're right north of 10 milligrams per liter, whereas groundwater is pretty low. So all of this is pretty characteristic of these two source waters. Going further, right, we're monitoring this over a 12-month period. For this study, or for what I'm showing today, we're only showing like 8 months for water quality, even less for the sequencing data. We'll talk about that in a bit. But for our temperature, right? We're seeing our groundwater fluctuate at about 21 degrees Celsius. Our surface water, we do see it start out pretty low, below 10 degrees Celsius. We started this study in the winter. So the source water temperature is pretty low, and then we see over the summer it starts to increase, right? This is to be expected, and primarily what's driving the dissolved oxygen levels in our surface water. And then looking just at bacterial loading, point out that this is a log scale, but we do have quite low bacterial loading for groundwater. We are below about 5,000 CFUs per 100 mils. We compare that to our surface water, which we tend to be 50,000 or higher. So we are orders of magnitude higher with our surface water compared to groundwater. And that, again, goes with our assumption for how these different water sources should be. And then just as a look, we did some sequencing at all these different levels. So source water, treated water, water in the distribution system. I want to just show what some of this looks like. So here we're looking at the groundwater microbiome. There are a lot of different organisms here. A lot of these make sense. A lot of these are anaerobic organisms. They are sulfur cycling organisms. So there's nothing too surprising here. We didn't really see a lot of opportunistic pathogens. We didn't see any enteric organisms. So again, a lot of this was what we were assuming we would see. I want to show this and point out that with our surface water, this is only a handful of samples. We had some issues when we were going to sequence, and the data just didn't come out correctly. So we don't actually have any data to show here for our surface water source, okay? But just highlight what this data tends to look at. And just as like a ballpark number, throughout our sequencing efforts, we identified 3,500 different strains of organisms. So that's kind of the scale of what we are looking at with this data set. So again, right, our groundwater showed signs of higher geological chemistry, low signs of bacterial activity. Surface water, very much the opposite, higher levels of bacterial activity, lower levels of geological chemistry activity. When we look at the composition of our groundwater, it tends to be a lot of anaerobic and sulfur-reducing organisms. Again, that's to be expected. It's what we typically see in aquifers. So all this is pretty standard. Went with what we were expecting, went with the conventional wisdom for these sources. So now we want to start going through and looking at like our actual treatment facility. So how does like these compliant water treatment systems impact all of this? So just as a note, we are monitoring the free chlorine residual. So our groundwater system, they do fluctuate a little bit with their application of free chlorine, but groundwater was maintaining at about 0.7 milligrams per liter, whereas we were getting nearly double that in the surface water of 1.3 milligrams per liter. Do want to note that because in our groundwater system, we essentially have a pump and then a bleed line to apply the residual disinfection. There's not a lot of contact time with groundwater. For the surface water, there's a ton of contact time. They tend to have a detention basin, and then they then will have additional chlorine residual leaving the treatment facility. So that's primarily why the chlorine residual is higher in the surface water, but we also need to note that it has higher disinfection time as well. So again, as I was saying, like they do vary how much they are applying this. Both systems tend to try to apply higher residual disinfection in the summer. So that's why you see it start to spike towards the second half of this data set. And then I wanted to point out here, because we're really going to start getting into this, but this blue box indicates what we have sequenced so far. So while water quality, we have a much larger data set. For what we're going to look at for sequencing, it's in this earlier period where our chlorine residual for groundwater was really low, and our chlorine residual for the surface water was much, much higher. So here we're seeing even more drastic differences between these water systems when we're looking at the sequencing results. So just as a general impact, how does this change our bacterial loading? Well, significantly, right? In our source water, which is, I guess I didn't include the legend, so apologize for that. That's going to be these red boxes on the left. We see that it's quite high for our groundwater and surface water, and that we're getting orders of magnitude reduction in our treated water shown in blue. So we are getting these significant reduction levels. Now, With surface water treatment, we generally aim for like a log 3 reduction of organisms, and we're right around there. We're going from about 50,000 to 50, so that is a reduction of 3 orders of magnitude. We are only getting about a log 1 to log 2 reduction in groundwater. Again, there's no requirement for groundwater, so these are still both compliant. I think it's interesting that we're actually achieving similar levels of bacterial loading post-disinfection for both systems. And then when we start looking at how our bacterial loading changes over time, right? Again, we see that our surface water maintains a relatively high level of bacterial content in the source water, but we are getting that effective reduction, particularly when we start to have higher levels of residual disinfection. Again, this blue square just indicates where we have the sequencing data so far. But one thing I want to point out with this groundwater is they more or less seem to trend together. So with our surface water, it seems to be that what drives our bacterial loading is residual disinfection. With our groundwater, it seems to be more that as the influent microbial loading changes, that also changes the effluent. And I think this is just a characteristic of how disinfection is carried out for these two different systems. Okay, so now we want to start like getting into the meat of this, and we want to look at these opportunistic pathogens. So for a lot of this, we just want to look at our detection frequency. So here we're looking at our treated versus source for the groundwater. And here we're seeing that we had one sample show up with Legionella in the source. That seemed to have disappeared in our treated water systems. We, again, have a very similarly low level of detection for Mycobacterium. And then with Pseudomonas, it is quite high. A few things I want to point out here. We will get into this a little bit later, but Legionella and Mycobacterium, those pretty universally are considered to be potentially pathogenic. Pseudomonas is quite diverse, so just because Pseudomonas is there, it's less likely to be pathogenic than the other ones would be. So while Pseudomonas is showing up in our source and treated water, it's hard to say at this stage if it's a concern. It could just be a natural organism. We don't, again, have the source water for our surface water. We had some issues with the sequencing, but we can just compare at the treated water, what are the exposure risks associated with these? So with our surface water, we do see, for the most part, a lot higher detection frequency of these pathogens, including Clostridium. We have about half of our samples detecting positive for Legionella, and we have 75% of our samples detecting positive for Mycobacterium. So our exposure risk from post-treatment is significantly higher than what we might see with the groundwater. And this does make sense. These organisms are typically associated with natural environment, so coming from surface water, they're likely present in the source water. So these are just breaking through our treatment process. So just some things to highlight here. We do see that our chlorine residual helps reduce our bacterial loading, both to similar levels. We are seeing that our groundwater post-treatment had a lower opportunistic pathogen loading, whereas our post-treatment surface water sample seems to have a higher risk for opportunistic pathogens. Okay. Again, these opportunistic pathogens tend to be found in surface water samples. Okay. So brings us to really the last major section of the system we want to look at, which is changes throughout the distribution system. So we could look at, there's a few characteristics for the water quality we're going to examine. The first one is how chlorine residual changes, right? So our blue dots here show the applied chlorine residual leaving the treatment facility. Our red dots show what it was measured to be at different points in the distribution system. For both of these, we do see it drop, and that's quite normal. There can be organic matter or microorganisms within the water that are going to continually consume some of that chlorine residual. But one thing we do notice is that with our groundwater, we are dropping the chlorine residual to be quite low. For these first sampling points, it is, for some samples, undetected. For other samples, slightly detected, but it is quite low compared to the other system. With our surface water, even in the distribution system, while we are getting quite a range across the different samples, On average, we're seeing a similar level of chlorine residual in the distribution system that we apply in the groundwater treatment system. So while we are seeing depletion, we're still maintaining a relatively high level of chlorine residual. And here we can actually see this shows up with how our bacterial loading changes. So in our surface water, we are getting similar or even below what level we had leaving the plant, right? So we're either maintaining the level or getting below the level like we see at some of these points. So we're not really getting any regrowth. It's maintaining or even disinfecting further. With our groundwater, on the other hand, because we are seeing that chlorine residual drop such a low level, we are getting significant levels of regrowth, where for pretty much every single sample we have, or sampling time point we have a significantly higher bacterial loading than what we had leaving the plant, so indicating some regrowth. And here we can actually see this by looking at the log growth. So log growth is just the ratio of the HPC we're measuring at different points in the treatment system over what we would see post-treatment immediately. And so any log growth that is over 0 indicates regrowth. Any log growth below 0 indicates no regrowth or even disinfection. So with our surface water, we're maintaining right about that 0 point, though some of these points, again, do drop below 0, indicating further disinfection. With our groundwater, we are seeing significant levels of regrowth. For a lot of these samples, we can get orders of magnitude higher, right? Just further indicating what we saw in the last analysis. And this seems to be primarily driven by chlorine residual. And so we can actually correlate our measured chlorine residual in the distribution versus our measured bacterial loading. And so for these two systems, we do see that there seems to be some trend, right? With our groundwater, we have a significant correlation, and it's moderately strong. As our chlorine residual goes down, we get less bacterial loading. We don't necessarily have a significant correlation with our surface water, but we do still see that level of trend. So we can actually go through and look at how this chlorine residual, it seems to be driving our lack of regrowth in the surface water system, whereas because our chlorine residual seems to deplete in our groundwater system, we start to get significant levels of regrowth. So we can start looking at what happens to the microbiome and these opportunistic pathogens. So just broadly looking at our microbial ecology, we see that we're not really getting a shift in species richness from our groundwater system, right? It's maintaining a similar number of organisms within our samples. With our surface water, though, we are getting a significant decrease in species richness, which is indicating to us that we are getting further disinfection. So we are getting removal of more organisms, a part of this residual disinfection. And then focusing in on these opportunistic pathogens, we'll examine surface water first. So we do see this trend of having higher levels of chlorine residual seems to deplete our bacterial loading. And we do see these blue bars are what we were measuring for these opportunistic pathogens leaving the treatment facility. And we see in every single case, our detection frequency goes down within the distribution system, right? So we are getting further depletion of these potential pathogens. With groundwater, we see the opposite, right? It goes with the trend of seeing this regrowth. We are actually getting Legionella show up significantly in a lot of these samples. We're getting Mycobacterium to show up significantly in a lot of these samples. Pseudomonas does decrease a little bit, but again, the ones we might be most concerned with would be Legionella and Mycobacteria. Those are the ones that tend to be more pathogenic. So we are seeing there be a spike in these two, even though they don't really show up in the treated water. I think I meant to take this one out. This just shows the same thing as before. So overall, what we're seeing in our distribution system is we are seeing that the chlorine residual, as it decays in both, but due to it being so low in the groundwater, we start to see a significant level of regrowth. Surface water had very little regrowth and in fact had at some point even further disinfection. related to this higher level of chlorine residual. And as part of this groundwater regrowth, we are seeing a lot of opportunistic pathogens show up. So what we want to explore with this is, it makes sense that a lot of these organisms show up in surface water. They tend to be part of soils and aquatic systems. So Legionella is pretty common in soils. Mycobacterium can be pretty common in these environments. Pseudomonas is pretty common in these environments. So showing up in surface water makes a lot of sense. They just bypass treatment, and the chlorine residual allows us to control their presence. What doesn't make a lot of sense is they don't show up very often in groundwater. These aren't geochemical bacteria. They aren't cycling sulfur or iron or other minerals. And so how are they ending up in the system, right? We detected them very sparingly in our source water. We didn't detect them at all in our treated water. So what is causing them to show up in our distributed water? So here we want to look at this phenomenon that we tend to see, which is you get a lot of, in these water systems, you tend to get two groups of microbiomes. One is in the bulk water, right? It's the water that's transporting throughout the pipe. That tends to be controlled by our chlorine residual. And then the other group is you can get a biofilm formation within pipe walls, where you can have some organisms kind of grow on the pipe wall, and under the right conditions, they might leave, but for the most part, they stay isolated in the pipe wall system. These tend to be more stable environments. They have mechanisms for how they handle things like chlorine residual. So here you can get organisms enter these biofilms and thrive, whereas they may not thrive in the bulk water exposed to the chlorine. We then get bacteria that will leave these systems when the shear stress is high enough, so it knocks parts of the biofilm off, or when the conditions improve, such as reduction in chlorine residual. This tends to be something that's hard to measure, our biofilm level within these water systems, because it's hard to convince a utility to let you cut into a pipe and sample it and then put it back together. So these are something that, while we know it's there, it's hard to monitor. So we have motivation in trying to figure out, is this the potential source for opportunistic pathogens? And if so, how can we measure it without having some invasive testing? So what we're going to do here is we want to figure out some way to determine what's in the biofilm, how that is impacting our pathogen loading, without doing some invasive monitoring. So we are taking our microbiome data, again, it's 3,500 or so different strains of organisms, and we're applying this Bayesian statistical machine learning model called Source Tracker 2. Here we essentially have two different samples. One sample is going to be our sources, and the other sample is what we call a sink, so what we're trying to identify the source being in. So the way this machine learning model works is it is trying to identify biomarkers within the source that we told it what a source is. It goes through and identifies biomarkers. These biomarkers have to be frequent and abundant. So if it shows up once in your set of source samples, it's not going to ping as a biomarker. It has to show up in a significant number of samples and at a significant concentration. Then what it does, once it identifies what these biomarkers are, it then looks for those biomarkers in your sink samples, and it says that those are coming from that source. Okay. What this particular source tracking model does is it also identifies what's not coming from a source. Most of the time, they identify just things that are from sources, and if it can't attribute it to its source, it kind of falsely attributes it to a source. So this model, if it's not a biomarker for a specific source, it just says it's an unknown biomarker. So we end up getting a couple different categories. So what we're doing here to try to elucidate this biofilm community, we are putting in only one source, and that is our treated water, right? So the assumption is that the water leaving the plant should be the water, what's in the water at those different time points. even if chlorine residual causes some of those organisms to decrease in abundance, or if the decay in chlorine residual causes those biomarkers to increase in abundance, they're still identified as biomarkers, and they would still show up as coming from that source, okay? So it's going to create an unknown category. These are all the biomarkers not from that source. And here we're going to assume that those are our biofilm organisms. So we have two sources. One comes from the treated water. The other one comes from an unknown source. For this analysis, we're going to assume that unknown source is indicative of biofilm. So just looking at our different source contributions, here we are looking at the total composition of our microbiome in these samples. So these two numbers will add up to 100. Same with the surface water. What we see is that obviously we should see a significant contribution from our treated water. It's pretty low. It's below 50 for both of these, and in fact for groundwater, we're below 25% of the microbiome coming from treated water. So we're getting over 75% of our sample coming from an unknown source, right? And again, we will assume that that is biofilm related. This does shift a little bit with the surface water, but we're still seeing a similar trend in that our surface water within the distribution system seems to be primarily driven by this unknown source. So looking into this a little bit further, we can then identify, we can see what was keyed as a biomarker, and we can see what is shared and what is unique between our two systems. So again, right, this shows very similar results what the previous slide showed. Our treated water source is quite low in the groundwater. The unknown source is very high in the groundwater. And then when we actually look at those biomarkers, there's a small portion of these that is shared between both groundwater and surface water. And that makes sense, particularly for the unknown source. This shifts a little bit with the surface water. We tend to get a lot more of these common microorganisms. So these are organisms shared between these two systems. And it's a lot more abundant in the surface water. So while we do see that obviously our source water has an impact on what shows up in the water system, does show that there's some universal shared organisms between these two. And then for this last bit of analysis, we're going to look at some rank abundance curves. I don't know if anyone's an ecologist, but essentially what we have here is we have on our on the y-axis, we have relative abundance of different organisms. On the x-axis, it's the species rank. The further to the right you get, the lower this should be because they're less abundant organisms, so they're not going to be the top organisms in the samples. Going to the left, right, you tend to get the more abundant organisms, the higher ranked ones. These are very typical curves. So looking at the groundwater, what we wanted to do is see what these organisms are. We highlighted the color of each of these organisms as being either blue for being unique to groundwater or being red for being shared between the two. And then I wanted to point out the different potential pathogen groups. So we have Pseudomonas. They show up a few samples within our treated group, but we don't see any Legionella, we don't see any mycobacteria. When we go to our unknown group, we see a ton of these potential pathogens show up. So we get a lot of Legionella, a lot of Mycobacterium, a lot of Pseudomonas. The different colors also show that we have some shared Legionella species between our two groups of water, and we have some unique ones for groundwater only. So what we're seeing is that kind of what we saw before, we aren't getting a lot of detection of these opportunistic pathogens within our treated water. And so they're not showing up in from our treated water. A lot of these opportunistic pathogens are coming from our unknown source, likely coming from our biofilm. So while our treated water might be good, it doesn't have this pathogen loading, these pathogens potentially being in the biofilm could cause them to regrow within the distribution system. Doing a similar analysis with our surface water, it just shows very similar trends. We have very little opportunistic pathogen loading leaving our water treatment facility. Most of our opportunistic pathogen loading is coming from this unknown group, right? This presumed biofilm group. So this highlights that while our assumption that groundwater is less biologically active has a lower risk of pathogen exposure, it's likely true, right? Groundwater does not carry these organisms. And then even where surface water does carry this, treatment can be quite effective at reducing their presence in the water. What we are seeing is that these are likely associated with our biofilm samples. So they're showing up in the biofilm where they can kind of live and survive chlorine residual. And when conditions are right, they can re-enter the water and cause some sort of exposure risk there. And then just some further analysis. We can do correlations between our suspected biofilm contribution and our residual chloride. So here again, we broke it up into our two different groups. We have our groundwater system, which for the samples we sequenced had a very low chlorine residual. For our surface water system, we tend to get a lot higher chlorine residual. We are seeing that for the surface water, this is a significant correlation, relatively strong. As we increase our chlorine residual, we get a lower contribution from that biofilm, right? Most of the drinking water microbiome is shaped by the treated water under those situations. So this just further shows that a lot of these potential pathogens, they're becoming a risk as we allow chlorine residual to decay. Okay. So overall, we saw that both water distribution systems were dominated by bacteria not found in the bulk water or not found in the treated water. So again, we suspected that this was going to be from biofilm contribution, where this was a high level of contribution to the drinking water in both the surface water system and the groundwater system. And this included those opportunistic pathogens. And then we also saw that the biofilm contribution increased as chlorine residual decayed, which just goes with our trend of seeing bacterial regrowth from the decaying chlorine residual. Likely that bacterial regrowth is stuff like this. There are opportunistic pathogens coming from the biofilm. So we're seeing like a universal, despite these systems meeting a lot of our assumption on what groundwater tends to be from a biological standpoint, what surface water tends to be from a biological standpoint, we do have this universal risk showing up related to post-treatment. Still have some open questions. How is Legionella entering the system in general? There seems to be some sort of universal shared microbiome between both of these two systems, despite having drastically different source microbiomes. So still further things to look into. So just as an overview, I think I was a little quick, but that's okay. Water leaving the treatment facility had relatively low opportunistic pathogen risk. That was something we saw in both systems. As the water left the treatment facility, we got chlorine residual decay. That is likely due to this interaction between the chlorine residual and the biofilms. But as that chlorine residual decay occurred, we got microbial regrowth just in general, and we got opportunistic pathogens regrowing as well, leaving the pipe walls and entering into the bulk water. Again, we identified these as being suspected parts of the pipe wall biofilm, and that while our groundwater had low post-treatment risks, with the managed lower chlorine residual, we saw that throughout the distribution system, we actually ended up with slightly higher opportunistic pathogen loading and opportunistic pathogen risks. So again, want to reemphasize, this is just a small part of this study. So a lot of what we are continuing with this study is we aren't finished sampling, so we wanted to capture seasonality variations. So we are still in the process of continuing to sample. We have only sequenced what I showed here, about half the samples. The plan, this is a student's thesis, is that he is going to sample for at least a full calendar year. So we still have about 8 time points to sequence to get a further analysis on temporal trends with these opportunistic pathogens. We need to do some further analysis phylogenetically. So while we identified several strains of Legionella, we identified several strains of Mycobacterium, it's hard to say if those are actually pathogenic, why wanting to call them potential pathogens or opportunistic pathogens. So we need to take that a little bit further and actually determine if those risks bear out with those specific organisms. We are actually in the process of sampling some pipe biofilm. So this is a difficult thing for us to do, but it's quite common that water mains break. They have to do some sort of maintenance. We have formed this great relationship with our 2 partner systems where they will actually, when they have a main break, they call us, we go sample the biofilm, and we're going to compare it with the results we got here, right? Ideally, we can find some way to identify biofilm without having to sample it. So those samples will contribute towards proving or disproving our suspected biofilm results. And then we are going to take this further. We collect a lot of samples. We are actually going to analyze for additional contaminants. So here we're just doing the microbiology of the drinking water. We want to measure disinfection byproducts and heavy metals as well. Oftentimes when you look at a lot of these drinking water studies, they tend to focus on one type of contaminant. Like I did here, we're focusing on these opportunistic pathogens. But what we would like to do is a more holistic assessment. So look at disinfection byproducts, look at heavy metals, and create a framework for minimizing total risk instead of minimizing risk from any one category. So this will be a part of this study as well. So I want to acknowledge a few of the people that helped on the study. So cities of Moscow, cities of Lewiston, they helped a ton. Great resources, and then had 2 students work on the project. Kyle Scholes, he's a co-author or co-presenter on this because this is his work, and then Benjamin Miller. And with that, I will take some questions.
Round of applause. What we usually do is to invite questions, or what we're trying to do is to first invite questions from Boise and Pocatello because it's harder for them just to jump in.
I guess I should pull up the chat too, right?
Yeah. A lot of times people put questions in the chat.
Have you considered sampling water, pipe biofilms, when the pipes are pigged? Might need a clarification on what you mean.
While Bruce is typing, can you hear me?
Yeah. I can hear you.
My connection is really bad right now. I'll try typing.
Oh, it's a question from Bruce.
Pigging is a process sending a pig, a physical device, through a pipeline to clean it. This is not something we have considered for this study, but actually glad you brought this up. We're setting up currently a lab scale version of this. That way we can more tightly control what's going on, so we can try to develop better management and engineering practices for minimizing some of these risks. And this is actually something we are wanting to do. That way we can do more frequent sampling of the biofilm as a way of studying that further. It's not something we considered with the water distribution systems that we're currently sampling, but it's absolutely something we are in development of doing. Is there a quantitative metric of the human health risks of these opportunistic pathogens? There is a developing field called quantitative microbial risk assessment. Some of you guys who are more heavily into risk assessment probably don't think it's as developing of a field. But this is something we can do. And the idea is it follows very similarly to like a risk assessment for carcinogenic compounds, where you develop a probability of infection or disease based on concentration and consumption. And so this is like a developing field. There's a lot of epidemiology studies on this to develop some of these models. Legionella, there is actually a wide range of different models that we could use, and we do plan on using this with Legionella to quantify that risk from exposure to Legionella. There's some for Mycobacterium. A lot of these other opportunistic pathogens, the data's not there yet. But for Legionella, Mycobacterium is something we could do. It's something that we want to do the phylogenetic analysis first to validate pathogenicity of these organisms, and then do this risk assessment. That's a great question. What impact do you think sample biomass or sequencing depth had in source tracker analysis, the ability to link some of the opportunistic pathogens in the distribution system with their source from surface water, surface groundwater, or treatment effluent? It definitely could have. When we did we did do some rarefying analysis for our sequencing samples. These are relatively low sequencing diversity, and we were able to get reads of some, apologize for trying to throw these numbers out. I don't remember exactly, but somewhere in the ballpark of like 10,000 to 20,000 was the average of reads per sample. That seemed to be sufficient for capturing diversity. And when we did the source tracking analysis, we actually rarefied to a sequencing depth of 10,000. So while obviously sequencing depth can play a big impact on how it relates to these, I don't think it played a major role here, though you do end up in this like philosophical debate of like, if you had unlimited sequencing depth, eventually you would find Legionella or something like that in the sample. But I suspect that our sequencing depth was sufficient for both of these analyses. Is there any evidence that the point of introduction of chlorine can affect accumulation of biofilm? For example, if a well is disinfected? That's a good question, something I've been considering. I don't know off the top of my head if there's any evidence of that for this. But that is a good question, something that is great for further investigation.
I'm going to try to jump in real quick.
Yes.
And this is sort of a related question, not so much to this particular work, but do you have a sense, are there sources that have been identified in domestic systems? Are there issues with pathogens in domestic systems?
Like within buildings and stuff, or?
Just within individual houses that are off of a domestic well.
Oh, like private wells?
Yeah.
There are, and generally when we think of groundwater issues, that's what we think of are privately owned wells. The issues are more traditional. Typically, Legionella is not as big of a concern. Generally, private wells, they don't do disinfection. And so the concern tends to be more like enteric, Giardia, Cryptosporidium, more GI-related organisms, primarily because there's very little effort on treatment for that.
Okay.
But yeah, absolutely, there's definitely some concern with private systems. Groundwater, why does the bacterial regrowth significantly drop off after 200 days? Seems counterintuitive. Let me go back. I'm also trying to make sure I don't hide the screen. Okay. It'd be easier to. There's a few different things we can look at. So this is source water quality. If we're looking at just the source water, groundwater, sorry, I'm trying to balance this. There's probably a better way for me to pull all this up. There we go. Oh my gosh, I'm really.
Oops. Yeah, try the little horizontal icon in the upper right.
Okay, this kind of helps. Okay, so here, if you're referring to the drop-off, it's hard to say. Part of this is this analysis is quite good at like giving us a rough estimation of bacterial loading, but this particular change, it's difficult for us to determine what is driving this. If we wanted to go through and look at the change post-treatment, do get slightly more regrowth here. Let's see, a little bit of drop off here. At this point, it might be difficult for us to determine. I would say broadly, chlorine residual dynamics seems to be what's impacting it, but there could be a bit more going on. For this one, this drop off here seems to be, we do have a slight uptick in chlorine residual measured there. But yeah, I mean, that's a good point. Something we definitely need to look more into. Part of this, let's see, I want to pull back up the chat. Part of this could be other factors compounding this, right? Here we're primarily looking at like chlorine residuals impact, but these other water quality metrics can impact it as well. And so further analysis connecting some of these trends we're seeing with additional water quality parameters. Another bit of motivation that didn't really go into here, hope to explore more with the student's thesis is to measure Legionella, to measure these other opportunistic pathogens. It's a pretty intensive process. And so if we can identify indicative water quality parameters for these things that make it easier for the different operators to identify, that might be a more useful way to monitor these types of pathogens. So probably look into other water quality parameters as well. City operators, building from your work to either optimize the timing of biofilm removal, or are they changing operations to allow biofilm flushing to avoid high-risk moments for public consumption? At the moment, there's no effort to update their current management practices. I think this is a very observational-based study. What we're trying to do is take some of these results and then try to develop better practices for them, but at the moment they haven't. There aren't plans to utilize these results to update their current practices.
Kind of going off of that question,
Yes.
How are you working with like, the Department of Health with these results? You just mentioned it's opportunistic, so maybe not to that step yet, but in terms of broader scale of human health effects, could these studies be applied to other water systems in Idaho or nationwide, or would this be unique to the water systems on the flukes?
So we are very specifically looking at just these two. As far as Legionella, it's almost universal. I referred to, I don't know if I went into too much detail, there's a major Legionella outbreak in New York City recently. Similar type of dynamic. So ideally, like these are case studies that we can apply elsewhere. I think what is a bit unique is we have, generally we think of Legionella mycobacterium as being things we see more in like warmer climates. I mean, it gets hot here in the summer, but I wouldn't classify Idaho as particularly warm. So this study shows the widespread of Legionella mycobacterium outside of those areas. And generally, groundwater systems aren't associated with Legionella, even though CDC reporting says it is. So yeah, broadly, while this is a case study, I think these results can be used elsewhere, particularly when we start going into an investigation for better management for these. We have not utilized we're not working with the Department of Health or DEQ on any of this stuff just yet. It's difficult because there's no like regulation on this, so like it's hard to enforce any action be made for these.
Do you think volume of the system would also have an impact? Like I'm thinking back to, what was it? The source 2 modeling of the proportion of source water. I think source tracker 2. Do you think size of the system could affect applicability? Or?
So for this study, Lewiston and Moscow are relatively similar sizes as far as their distribution systems and their water capacity. Lewiston's quite interesting by itself, but so there's a few answers. I think it almost ties into a question related to homes. So volume of the system doesn't necessarily itself impact, but one thing we do see that impacts a lot of this is size of your infrastructure. Larger pipes tend to have less relative biofilm. Smaller pipes tend to have relatively higher biofilms. It's generally why I just told the so generally, like, we're looking at the distribution system, but like another big concern is actually plumbing within homes and buildings, because pipe size is much smaller. The pipes we were sampling, both of these systems are about 6 inches, whereas in your house it's under an inch. So it tends to have a lot more biofilm. You do have, now if you're talking about like, well, volume for the system itself doesn't necessarily impact this. Smaller municipalities, more rural systems, likely have a higher burden to manage this, because one part of this is larger communities, the water tends to become less stagnant, so it ages less. Chlorine residual maintains a lot easier. Smaller communities, the water tends to get a lot more stagnant, chlorine decay occurs a lot quicker, and you start to get a lot more regrowth like that. So yeah, I wouldn't necessarily say like the volume of the system, but like population drives this a lot too. It's particularly from like a management side.
It'll be interesting to see summer trends with irrigation.
Yeah.
Or bans irrigation.
Yeah. Yes. I want to see, was there another question?
I had one.
Yes.
I don't know if this was clarified, so I was just curious. When you were talking about like the machine learning module and like it was just helping to like trace the sources within the system, is there like an evolution to that that's going to be like a predictive tool, like something that could like create a hotspot sort of thing for a pathogen regrowth in the system to help those risks?
Yeah, this is part of our analysis. We're still collecting data. This particular machine learning model, it's more retroactive. We take our already produced data and we try to produce a biomarker profile for source analysis. But we can potentially take those results, run it through. There are additional machine learning models that we would prefer to use for predictive capabilities, like more of like a random forest or neural network approach, where ideally we could take easy to collect water quality parameters, alkalinity, pH, chlorine residual, temperature, as input parameters to then detect hotspots, potential hotspots. That is an approach we're trying to develop. Because again, not every utility has the capability to do sequencing, so we want to make this a lot more broadly usable instead of being more academic. But yeah, it's something we're actually trying to utilize a lot of this data for, is try to produce those tools.
Thank you.
Okay, very good question session.
All right.
Okay, you want me to?
But maybe just check real quick. I know we've gone over time, but just see if anybody maybe in Boise has a question. I don't know if, sometimes it's hard to jumping.
Oh, hi. Can you hear me? Yes. No. Hello. Do you hear me?
Yes, yes.
Oh, great. My question was, do you think there's something about the groundwater or the surface water that makes the chlorine like decline more, or is like the treatment put in the surface water just use more chlorine?
This is a fantastic question, because we are trying to explore this paradigm. General thought is chlorine is just a good oxidizer, so you have a lot of organic matter in surface water that causes chlorine decay. It's why surface water treatment has extensive chlorine contact time, order of hours, whereas for groundwater treatment, they are just dosing the chlorine instead of letting it react. So the general paradigm is that surface water has a lot of organic matter. the organic matter consumes the chlorine. It's part of the reason we have concerns with disinfection byproducts in surface water. Groundwater has very little organic matter, so generally the chlorine consumption is quite low. One thing we want to start looking at is the development of disinfection byproducts post-treatment, because one concern is that this biofilm we're seeing that's pretty consistent in both water systems, that is a huge sink of organic matter that could further consume the chlorine and potentially produce disinfection byproducts as well.
Thank you.
Okay.
Thanks, Clifford.
Thank you.
Appreciate it. It's great hearing what you do.
I'll let you finish.
Oh, that chair's helpful. So, yeah. All right, thanks, folks. We will see you next week. And we have another new civil engineering professor up here from the University of Idaho who will be presenting, I believe, live from Moscow, and that's Angel Monsalve, who I can't remember the exact topic, but it's going to be something related to ecohydraulics. So it's the best I can do. All right, see you next week.